Hello, everyone. Today, it's my great honor to discuss a very cool topic with you all. How to give our AI models a memory, just like we have. Imagine if a model could not only learn new knowledge, but also remember what it has learned and retrieve it whenever needed. What would that look like? That's the memory-augmented networks we're going to talk about today. More specifically, we'll take a deep dive into two classic models, DKVMN and its upgraded version, SKVMN. You can think of them as a super notebook we've equipped the model with. Let's see how this notebook works and what surprises it can bring to our research. In today's presentation, we'll follow a clear roadmap. First, we'll revisit the bottleneck encountered by its predecessor, the DKT model, which is the memory interference problem, and see how DKVMN cleverly solves it. Next, we'll dissect the core concepts of DKVMN to understand how its notebook is structured. For a more intuitive feel, we'll walk through a specific calculation demo step by step to see how it reads and updates knowledge. Then, we'll explore the model's key parameters to see what it actually learns during training. After that, we'll introduce its upgraded version, SKVMN, to see how it's further optimized. Finally, and most importantly, we'll discuss why this model is so important for our research and what unique value it can bring. Hopefully, this agenda will give you a comprehensive and in-depth understanding of this powerful tool. Let's start from the root of the problem. Before DKVMN, the mainstream model was DKT. DKT's way of working is a bit like kneading all knowledge into a single dough, a single state vector. Imagine you've studied math, Chinese, and English, and all that knowledge is jumbled in your head. What problem would that cause? Exactly, knowledge confusion and memory interference. When you try to recall a math formula, an English word might pop in, and your brain becomes overloaded. That's the pain point of DKT. So how does DKVMN solve this? It's very clever. It designed a loose-leaf notebook for the model. This notebook has 2 pages. The left key matrix is the table of contents, listing the names of each knowledge point, like the Pythagorean theorem or past tense. The right value matrix is the specific content, recording your mastery level of each knowledge point. This way, knowledge and mastery state are separated. The model can, just like we flip through a book, use read and write operations to accurately find and update a specific knowledge point without affecting other content. This perfectly solves DKT's memory crosstalk problem. Now let's take a closer look at the internal structure of this loose-leaf notebook. It mainly consists of 5 core parts working together. First is the key matrix, which you can think of as the table of contents of the notebook, clearly listing the titles of all knowledge points. Second is the value matrix, which is the content page of the notebook, dynamically recording your mastery level of each knowledge point, from completely clueless to proficient. When the model encounters a new question, it calculates a read weight, which is like our attention. It determines which entry in the table of contents we should look up. Then, the model reads information from the content page based on this attention weight to form a knowledge state, which is like a snapshot of our current knowledge level. Finally, when we learn new knowledge or get a question wrong, the model needs to update the notes. This is where the erase vector and add vector, the editing tools, come in. They are responsible for erasing old, inaccurate mastery states and adding new, updated ones. These 5 parts work together to allow the model to memorize and learn in an organized and precise way, just like a human. We've talked a lot about theory. Let's look at a concrete example and walk through the calculation process. Suppose our system only has 2 knowledge points, A and B. Our notebook is ready. The table of contents page, key matrix, has the titles of A and B written down, and the content page, value matrix, is initially blank, indicating we know nothing about these 2 points. Now we enter step 1. The student attempts to answer question Q1, which tests knowledge point A. First, the model calculates a read weight. It will see which of A or B in the table of contents Q1 is more similar to. Obviously, it's most similar to A, so it gives A the highest weight. Next, the model reads our mastery level of A from the content page based on this weight. Since it's the first time, it reads 0. Then the model predicts the probability that we will answer Q1 correctly based on this mastery level, which is certainly very low. Finally, suppose we get it wrong. The model will initiate the update procedure using the eraser, erase vector, and pencil, add vector, to modify the mastery level of A in the content page, adjusting it from 0 to a slightly higher negative number, indicating, I tried but failed. See, this is a complete learning feedback cycle. Okay, let's continue with step 2. This time, the student attempts to answer question Q2, which tests knowledge point B. Similarly, the model will calculate the read weight, giving B a high weight this time. Then it reads the mastery level of B from the content page, which is still 0. The prediction result is naturally also a low accuracy rate. But this time, suppose the student gets it right. The model will update the mastery level of B in the content page, raising it from 0 to a positive number. Here's the most crucial point. Notice that when updating B's mastery level, A's mastery level is completely untouched. This is what we call zero crosstalk. Learning knowledge B does not interfere with our memory of A. It's like writing on page B of a notebook. You will never accidentally write on page A. This is the essence of how DKVMN solves DKT's pain point. So, what exactly is the model learning during training? Let's look at its key parameters. First, the key matrix, that table of contents, is learned by the model itself. It discovers the unique intrinsic features of each knowledge point. Second, the value initial matrix, the initial knowledge level of a new student, is also learned by the model. It knows roughly how much a novice understands. Then, all the neural networks used to calculate read weights, predict results, and generate erasers and pencils. Their weights and biases all need to be learned. Of course, there are also some hyperparameters we need to set manually, such as how big the notebook should be, memory size, how fast to learn, learning rate, and so on. There's a very important detail I need everyone to note. The content page, value matrix itself, is not updated through backpropagation. What the model learns is how to initialize it and how to use the eraser and pencil to update it. This is a very clever design. DKVMN is already great, but does it have any shortcomings? Of course it does. Its biggest limitation is that it's a bit forgetful and ignores the sequence of learning. It treats each learning session as an independent event, which is inaccurate in reality. What we learn today is definitely influenced by what we learned yesterday. To solve this problem, SKVMN came into being. Building on DKVMN, it adds a sequential controller, which you can imagine as a particularly smart teaching assistant. The job of this assistant is to review the student's entire learning history. For example, DKVMN is like a direct page turner. You ask it about question A, and it flips directly to page A. SKVMN, however, has an assistant by its side who first looks at what you've studied in the past and which questions you got wrong, then decides whether to flip directly to page A this time or first consolidate previously related knowledge points before coming back to learn A. This assistant makes the model's decisions wiser and learning more efficient. Having said so much, what practical value does this model have for our research? I believe there are 3 main points. First, it naturally supports multidimensional ability decoupling. Because each memory slot can correspond to a specific knowledge point or skill, we can perform very fine-grained diagnosis of a student's abilities rather than giving a general score. We can clearly know which specific knowledge point they haven't mastered well. Second, it has extremely high interpretability. Traditional deep learning models are often called black boxes. We don't know why they make a certain prediction, but DKVMN/SKVMN is different. We can directly open its notebook and see the numerical mastery level of each knowledge point. This makes the AI's decision-making process more transparent than ever. Third, it can easily integrate with multimodal data. In addition to answer records, we can also integrate other information, such as question difficulty, learning duration, the student's emotional state, etc., into this memory system, allowing the model to have a more comprehensive understanding of the student. All right, let's briefly recap the core content shared today. The core idea of DKVMN is to give the model an external notebook, storing knowledge itself and the mastery level of knowledge separately, thereby achieving precise reading and writing and solving the memory interference problem of traditional models. During training, the model mainly learns three things: what the table of contents of knowledge looks like, what the initial level of a novice is, and how to intelligently perform read, write, and update operations. Its upgraded version, SKVMN, by adding a sequential controller, enables the model to learn to review history and consider the order of learning, thus becoming more intelligent. In summary, DKVMN and SKVMN provide us with a powerful and interpretable tool to simulate and analyze the human learning process. Thank you all again for your attention. I hope today's presentation has inspired your research or work. If anyone is interested in this topic, we can continue to communicate in depth after the session. Thank you all.